Alright, hello everybody. We're back in section 5.1 and we're going to look at polynomial functions. So first of all, a polynomial is something that can be written in the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1x plus a naught, where here all the an's are some kind of real numbers. The important thing is that the exponents on variables are either 0 or positive whole numbers, so no fractions, no decimals. And here's all the important stuff in terms of the polynomial. Its degree is n, its graph is smooth and continuous, which means you can draw the whole thing from left to right without lifting up your pen, and there's no sharp points, there's no corners, there's no cusps, it's smooth. The maximum number of turning points is one less than the degree, and that's the maximum. You don't necessarily have to get that many, but that's the most you could have. A zero of even multiplicity touches the x-axis, where a zero of odd multiplicity crosses. And the n behavior for large values of positive or negative values of x, graph behaves like this first term with the coefficient. So that's what the degree is so important. This term will dominate all the other terms when we're looking at large values. So let's take a look at an example. Okay, so here I have a polynomial. F of x equals x squared quantity x minus 2 quantity x minus 3 squared. Okay, and the question right now is, what's the degree and n behavior of this polynomial? So this right here is written in factored form. It's definitely factored. Factored form is nice because it tells you the zeros and the multiplicities. But in order to get the degree and n behavior, I have to expand this guy out. So that's what I'm going to do. I'm going to take this guy and I'm going to expand it out so it's written in like a standard form. So the first thing I'm going to do is I'm going to take this guy and write it twice. And I'm going to start to FOIL all this stuff out. Now, this is one way to go about it. So here, if I FOIL, I get x squared minus 3x plus 9, x squared x minus 2, x squared minus 6x plus 9. And then multiply this out. So we get x squared, distributing the x in here to all values, we get x cubed minus 6x squared plus 9x, and then running the minus 2 in, minus 2x squared plus 12x minus 18. Let's see, make ourselves some room here. Equals x squared, x cubed, minus 8x squared plus 21x minus 18. And lastly, I'm going to run the x squared in. So I get x to the 5th minus 8x to the 4th plus 21x cubed minus 18x squared. So here I can see, well, the degree, biggest exponent is a 5, and the n behavior is going to be x to the 5th. So that's the nice thing, is once it's expanded out, you get these for free. Now this is like a lot of work. Another way to look at it is, well, if I go back up here, if I think about, okay, if I expand this out, the biggest term I'm going to get is that x squared plus a bunch of smaller terms. So I can focus on that x squared. Then when I multiply these all together, again, I'm going to do x times x squared. It's going to give me x cubed and a bunch of other diminished terms. Finally, when I multiply the x squared in, that's what's going to give me an x to the 5th. Remember, you just need the term with the biggest degree on it, biggest exponent, in order to get the degree. And same with the n behavior. So you don't necessarily have to do all this work in order to see it. You could probably say, okay, just thinking about multiplying all this stuff together, well, the biggest x I'm going to get is x squared times x times x times x. So that's your x to the 5th. And if there was a coefficient that would come along to the right, that's also going to be the n behavior. Okay, so let's look at some other things with this polynomial. Okay, now let's look at this. List each zero, its multiplicity, and whether it touches or crosses the x-axis. That is really easy to do if it's in factored form. That's the whole point of factoring, is it gives you those zeros. So here I have a 0 at 0, because you have this x squared term out here. Its multiplicity would be 2, because that's your exponent. And since 2 is even, it's going to touch. Next 0 is here at the number 2, because remember, it's got to be opposite. You've got to make this middle thing turn into a 0. Its multiplicity is 1. Remember, you can always put a 1 here. And since 1 is an odd number, it's going to cross. And its last 0 is at 3. It has multiplicity of 2, and it's going to touch as well. It's really easy if it's factored, and if you have a problem that's not factored, you need to factor it in order to find the zeros and the multiplicities. Okay, let's look at another question. Okay, now we want to determine the behavior of the graph near each x-intercept. So remember, x-intercepts are also zeros. So our x-intercept here, we have x-intercept at x equals 0, at x equals 2, and at x equals 3. Those are x-intercepts because x-intercepts are zeros. Okay, so let's look at this first one. So at x equals 0. To determine the behavior near each intercept, we plug this in for all factors except the one that make it is equal to 0. So except 0 for the one that will make it 0. So this causes it to be 0. So what I'm going to do is I'm going to plug in 0 in for all these other factors. X squared, parenthesis, 0 minus 2, and 0 minus 3 squared. Now I'm going to see what this is. So this is x squared minus 2 minus 3 squared, which equals minus 3 squared is 9. So finally, at this x-intercept, the function's going to behave like minus 18x squared. So you plug it in for all of them except for the ones that zero out. So let's see what happens at the x equals 2. So again, I'm going to plug in 2 into all the factors except the one that causes it to be 0. So I got 2 squared, parenthesis x minus 2, that's the 0 one, and 2 minus 3 squared. Let's see, this is 4, parenthesis x minus 2, and this is minus 1 squared, which is 4 times x minus 2 times by 1. So near this value, it's going to behave like that. Okay, last one. Okay, let's see what happens around 3. So again, plugging 3 in for all x's except the one that would cause it to 0 out. And here I get 9 times 1, x minus 3 squared. So around here, around this x-intercept, it's going to behave like a quadratic function that opens up. Okay, finally, let's take a look at the graph. Okay, so first I'm going to mark down each 0. So I have a 0 at 0, I have a 0 at 2, and I have a 0 at 3. So I mark down each 0. And then what I like to do is I like to make a little indication by each 0 whether it touches or crosses. So remember, you can go back and look at the list, but at 0, it's multiplicity of 2. So around this guy, we're just going to touch. At 2, it's an odd multiplicity, so we're going to cross. And at 3, it's another even multiplicity, so we're going to touch. And now, you've got to draw a graph that's smooth and continuous. You just have to know how to start. So there we're going to look at the end behavior. Remember, the end behavior of this function, it's going to behave like f of x equals x to the 5th. So I always start and work some far from the left. We're either going to approach this 0 from the bottom or the top. So the way to tell is I'm just going to plug in some big negative number into here. And I don't even really care so much about the value. All I want to know is whether this turns into positive or negative. And minus 100 to the 5th power is definitely something negative. So I know when I'm plugging in something way out here, I get a negative value. So here we go. I'm going to draw a continuous smooth function, and I'm going to just use the multiplicities, and that should give me a good graph here. So I need to approach this first 0 from negative because this value is negative. I get to the 0, I touch, I cross, and I touch. Arrows at the end. Now we can get more accurate with it if we actually plugged in 1 and saw what the value was, plugged in some value between 2 and 3, etc. But this is a pretty good graph of this. And last thing, how many turning points are there here? Remember, we could have a maximum. We're supposed to have a max of 4. But in reality, this graph has 1, 2, 3, 4. We actually have 4 turning points. Well, that's good because that's the maximum amount we could have. Remember, turning points are where you're going to have a max or a min. So we've got one there, 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 and there. Okay, some of the problems in the homework I'm sure are going to have to ask you to give it in standard form. You're going to have to factor it to get the zeros, but you should all be able to do that. If you're weak on factoring, go look at those videos from factoring. But that should do it for this video. Good luck. Smiley face.